Good evening, students. Today we are going to see about the Bohr-Sommerfeld quantum condition to find out the energy levels of a potential well. As we all know that from the modern physics or from atomic physics, we know that um, first we have introduced the introduction to the nucleus and structure of an atom was given by first J.J. Thomson. Later, the drawbacks has been overcome by the Rutherford. He derived an atomic model and he says how the nucleus and how it is its structure, what are all the charges present inside the atom. And later, he also committed some of drawbacks, and this has been overcome by the scientist called Bohr, and he derived an model called Bohr atom model. In his structure, in his atom model, he says that the electrons revolve around the nucleus, and when the electrons are moving from one energy, higher energy to the lower energy, it will emit some radiations. These are all the postulates taken by the Bohr. And later, they are derived by the Sommerfeld, and they are find out the conditions they are applying to an applications. The applications. The next given by the vector atom model. Then Pauli's exclusion principle. All these find out the drawbacks in the Bohr-Sommerfeld models, and they given the new atom model called vector atom model, where we can easily find out a number of electrons present in an orbit and the shells. Okay, so this when you are applying to an applications. Okay, so Bohr-Sommerfeld quantization, because when the vector atom model, we have the two postulates called spatial quantization and the spinning of electrons. Okay, so we need a quantization. So this, by using the Bohr and Sommerfeld conditions, equations, we are applying to an applications called a potential well. Potential well. We know that there will be a barrier when a potential well, and these electrons will travel from one place to the other place through a tunneling process that you all know from the rectangular potential barrier. Okay, the same conditions that we are taking, and using the quantization principle, Bohr-Sommerfeld conditions, we are deriving an energy, we are deriving an equation for the energy levels. Okay, for that now consider a potential well where we are having three different regions, and the region 1 and 3 have the same conditions, whereas 2 it is completely filled. Okay, so we can take this condition. Regions 1 and 3 are classically forbidden. That is, the electrons are traveling from the region 1 will fully not transmitted to the region 2. So some of gets reflector and some of gets transmitter. And while in 2 it is fully transmitting, at the boundary condition of 2, ending boundary condition, it gets again transmitting and the reflecting. The transmitter lights are moved towards the region 3. Okay. Now, so as a particle of energy E executes a vibrating motion between the points x1 and x2. Okay, so quantum mechanically we give these conditions, these wave functions as u1, u2 and u3. We are denoting that. Some way we are denoting the quantum wave functions as u1, u2 and u3. First we take the conditions of region 1 and 3, where they having the wave function as u1 equal to this equation, that is d1 divided by p of x of whole power half exponential, this equation 1. And equation 3, which gives the standard equation of region 3, where it is exponentially decreasing function, behave like a decreasing function. We can say it is a minus half, because it is in the third region where all the lights are passing towards a potential well, where it have a no boundary condition. So it's traveling somewhere else, we don't have any boundary condition, so we are saying it is an exponentially decreasing function. While we are switching over to the connecting formula between the regions 1, 2 and 3, we have that equation 3 and 4, where this is called as a connecting formula given by our scientists, great scientists, both Bohr and Sommerfeld. Okay, so d1, we have that equation 1, that is equated, this transformed to the equation 2 d1 divided by p of x half cos value, because we have that cos component in this region, and in the region 3 also we have the cos component. And the region 2 has a single wave function. You please be there. The region 2 has a region 2 has a single value wave function, and we equating this equation 3 and 4, equating this equation 3 and 4, we get the final equation, and deleting all the equal components, and we have that equation. And in that equation you use d is equal to d2 by d1, and let us derive that equation 5 for a limit of minus from the limit x2 to x, where we can derive the equation for the region 2. Okay, so this argument of the above equation function will give the cosine left hand side and can be written as like equation 7. So finally we can derive from the equation 7, we can derive the all these equations, and we have derived the equation for region 1, 2 and 3 for the energy levels, for different energy levels, and then for closed integral we can give the above equation, that is final equation, as equation 11, where h of n plus half. We all know that for a simple harmonic oscillator, the final equation, the energy, we can give it as an h cross of n plus half. And the final Bohr radius formula, where we have studied in the atomic equation, atomic physics, we have studied that Bohr equation, which is also En into n plus half. That is, energy E is equal to h cross into n plus half. It means that what it says, that what it implies, that the energy always will not be equal to 0, where n is a principal quantum number. If it is, it will not be equal to 0. If it is 0, then the equation will be half h cross. Half h cross. So the always the energy will not be equal to 0, and somewhere we are having the energy for the particular electrons or a particle that is traveling from the region 1, 2 and 3. So this was given by our Sommerfeld quantization condition for a potential well. Thank you.